Deliver structured caps and line lessons for high school subjects including mathematics, physical sciences, life sciences, geography, business studies, history, accounting, English, Afrikaans, and others.
For the intermediate and senior phases, we offer expert teaching in natural sciences, mathematics, social sciences, English, and EMS designed to build strong academic foundations.
Access the distinction material books by clicking join button on our YouTube channel or download Thundereduc app on Google Play Store for all our study material and past exam papers.
Thundereduc offers extra classes for rewrites, old curriculum, and other students from grade 4 to grade 12 through online and physical classes.
Subscribe to our YouTube channel Thundereduc for reliable curriculum-focused learning and stay updated with the latest educational content.
Please like, share, and turn on notifications so you never miss a lesson.
Visit us at www.thundereduc.com
or call 0786 636 613 or 084 833 1738 for more details.
Thundereduc, we focus on quality.
Good day to you, great health learners. It is my pleasure to invite you to the discussion for the Gauteng Junior Examination Geography Paper 1. This is the paper that was administered for the Junior Examination Paper 1. We are going to go through the discussion of the paper, and we are going to highlight the possible responses that would be satisfactory in answering the given set of questions. And also we are going to elaborate on how best we can approach those questions, and also why we are saying the responses that we are giving are the best responses in the attempt to assist you in attaining a better grade at the end of your study session, which is in your final examination by the end of the year. So that is our paper. As usual, our geography paper, our paper 1 has got 150 marks, which are supposed to be attained in 3 hours time. And we check on our setup of the paper. It's always the same. We have our climate and weather, which is 60 marks. Question number 1 in section A, theory section. Then we also have question number 2, which is geomorphology, which is specifically fluvial geomorphology, which is has got 60 marks, which is question number 2. And in both papers, we have question number 3, which comprise of geographical skills and techniques, what we generally call our map work. Right. So without wasting much time, let's go into our questions. We start with section A, question number 1, climate and weather. Right. We have our first question. It is an image showing a mid-latitude cyclone. Right, if we check there, we can see that that is a mid-latitude cyclone shown by the cold front ahead of point A, advancing towards C, and we also have our warm front, which is in between C and B. Right, so we want to use that satellite image to answer our questions. What is the general direction in which this mid-latitude cyclone moves? We understand that our mid-latitude cyclones, they are always influenced by the westerlies. Our mid-latitude cyclones, they happen in the planetary belt of our westerly winds. So they are driven by, or they are influenced by, the westerlies. That doesn't change. Our mid-latitude cyclones are always from west to east, which is the opposite of tropical cyclones, which move from the east to the west, because they are influenced by the tropical easterlies or the trade winds. But in this instance, we are worried about the mid-latitude cyclones, which are influenced by the westerlies. They are moved from west to east because of the influence of the westerly planetary belt. Right, why is there more cloud cover at A than at area B? If we check here, at A, there is more cloud cover than at area B. Why is it that there's more cloud cover at area A? We are seeing that area A is just along, or is just slightly behind the cold front. and area B is ahead of the warm front. So what makes it favorable for dense cloud development along area A, which is just adjacent to the area of the cold front? It is because there is rapid upliftment of air at the cold front. If you check the cross section of the cold front, we see that our mid latitude cyclone will have the cold front like this, and we'll have the warm front. Unfortunately, let me redraw that. The warm front is not steep. We are seeing the cold front is having this kind of a slope, which is steep sloping. And then the warm front, we have a gentle slope. So for this sake, we are saying our cold front is having a steeper slope, and which means the air is going to be forced to rise almost vertically. There are strong updrafts of air because of the steepness of the cold front. So it means the clouds which are going to form here are going to be denser. Why? Because there is rapid upliftment. The upliftment is immediate because of the slope of the cold front. Right. Let's move on to the next question. Area A, we will most likely have dash clouds. What kind of clouds will we experience in area A? The type of clouds are determined by the nature of the steepness of the front, which is influencing the formation of the clouds ahead of it. Our cold front is very steep, like we can see here. This is a steep sloping front, which means the air which is being forced to rise is going to rise almost vertically, and it means the moisture is going to condense and create towering clouds of large vertical extent, which we call the cumulonimbus clouds. That is typical of the nature of clouds that are going to be realized. We have typical of cumulonimbus clouds forming. Right, we move on to next question, number 1.14. What will happen to the wind direction when the cold front passes the southwestern cape? When the cold front is passing the western cape, what is going to happen there is the wind is going to change from a northwesterly direction to a southwesterly direction. You will check on the rotation of the system. The system rotates in a clockwise direction. So it also means the wind is going to change from a northwesterly to a southwesterly direction because of the clockwise rotation of the weather system. Right, C is located in we are looking at area C. Let's go back and look at area C. We are seeing this is our warm front. Here we have the warm front and we have the cold front here. So we are looking at the area which is in between. We are saying our weather system is rotating in a clockwise direction. So an area which is in between the cold front and the warm front is the warm sector. So if we are looking at our C, we are seeing our area C is located in the warm sector, which is response C. Right. Number 116, it says, why will the temperature at C decrease as the cold front passes? We are saying this is a warm sector at C. But as the cold front passes C, we are seeing the cold front is advancing. And it is going to pass area C. We are seeing that this is a warm sector where there is warm air, but ultimately after the passing of the cold front, C is not going to remain a warm area, it's going to be a cold area. What will make it a cold area? What will change the weather conditions around C is because of the situation of the cold air behind the cold front will arrive. We are seeing behind the cold front here, there is cold air. And the cold air is pushing in this direction, which means it is ultimately going to push the position of the cold front until it passes C. Once the cold front passes C, it means C is now occupied by the cold air, which is behind the cold front. And that will automatically cause a decline in the average temperatures around area C. Let's go to number 1.17. The occluded front in a mid-latitude cyclone is formed when we talk of an occlusion, we are saying we have a situation like this. This is our cold front and this is our warm front. When we have an occlusion, we are having this situation. This is what we call an occlusion. How does this happen? How do we tend to have these two fronts being presented on one line? A cold, a warm, a cold on one line. It happens when a cold front overtakes a warm front. When ultimately the cold front catches up. Because initially we are saying using a cross section, we are saying the cold front will be there. This is our ground and the warm front will be there. So we are saying this is the cold front and this is the warm front and this is the warm sector. But because of the effect of cold air which is behind the cold front advances faster compared to the warm front. The cold front moves faster, so which means it is going to catch up. The cold front will come there. Now, because it catches up with the warm front, this is the occluded front. It happens because the cold front has managed to catch up with the slower warm front. Cold front is faster. Why is it faster? It's because this air is denser. Denser air is pushing towards less denser air. The warm front has got less denser warm air. And because of that situation, warm air cannot effectively push towards colder air because ahead of the warm front, there is cold air again. So for that instance, we are saying the cold front moves faster or it pushes faster towards the warm sector than the warm front moving towards the cold air ahead of it. And as a result, we tend to find that the cold front catches up with the warm front and that results in an occlusion. Right, that was question number 1.17. Let's look at the next question, question 1.2, it's a matching column question. We are going to go through the questions as quick as is possible. Number 121, it says tropical cyclones may form when sea surface temperatures are above. Right, the required temperature or the temperature which facilitates the formation of tropical cyclones, we need warm ocean, we need warm sea temperatures which are above 26.5 degrees Celsius. In the southern hemisphere, tropical cyclones rotate. The rotation of a cyclonic weather system in the southern hemisphere is basically clockwise. All low pressure systems, if you have a low pressure, remember a cyclonic weather system is a low pressure. If you have a low pressure cell, air circulates into a low pressure cell in a clockwise direction. And if we have a high pressure cell, which is an anticyclone, the air moves out in an anti-clockwise direction from an anticyclone. That is typical of southern hemisphere. And the opposite is very true for the northern hemisphere. Right, the center of a tropical cyclone is called there. What is the name of the center of a tropical cyclone? The clear part of the tropical cyclone is the eye of the system, where there are stable conditions, clear skies, and clear and fine weather because of the descending air at the mid of the system. Right, tropical cyclones gain latent energy from, where do they get latent energy? Latent heat is released because of condensation process. When condensation takes place, there is a release of energy which is called the latent heat. Latent heat of condensation, that is where we find the latent heat or the latent energy being released. Right, number 125, it says a tropical cyclone loses strength when it moves. How does a tropical cyclone lose its strength? When it moves over land. Why does it lose strength? The tropical cyclone is going to strengthen because of additional moisture being added to the system. And also because of the smoothness of the surface over which it is moving. if it moves overland, there is no more moisture being fed into the system, which is going to condense and add more latent energy. And also, as it moves overland, the land is an uneven surface compared to water. Water is even, is level, and there are no rugs over water surface. But as we compare overland, we have uneven surfaces, we have mountains, we have valleys, so the system will weaken because it is now moving over an undulating surface or over an uneven surface, which makes it lose its potential to gain energy to move faster. And also, we look at it from the perspective of frictional drag. It is going to be dragged by friction as it is moving over a solid surface which is rugged. So as you move over land, it means it is going to lose its strength. Right, number 126, it says the strongest winds in a tropical cyclone occur in the strongest winds, we find them around the wall of the system, which is why those who remember, we say they are updrafts and the eye is at the center. The strongest winds are experienced just immediately around the eye, which is the wall of the system. And also, if you check the nature of clouds, we have towering clouds developing here because of strong updrafts. But as we go further away, we tend to have low-lying clouds from the wall of the system. So the eye wall is the one that experiences the strongest winds. Right, we move on to the next question. Tropical cyclones cause damage through high winds, it's correct, through heavy rain, and also through storm surges. Storm surges will happen along the coastal areas because of the build-up of pressure, which is caused by the circulation of the air. The water in the ocean is going to build up and is going to overflow the coastal areas, which we call the storm surges. The storm from the ocean is going to push, because of the gravitational effect, is going to build up and increase the level of the sea. And ultimately, water is going to be pushed out of the coastal areas and is going to cause damage along the coastal areas, what we call the storm surges. Right, we move on to number 128. It says tropical cyclones move from dash in the southern hemisphere. Our tropical cyclones, we've talked about it, from east to west. Right, that was question number 1.2, a matching column question. We move on to question 1.3. Right, we want to do the interpretation of the illustration before we answer the questions. Right, we are seeing this is a typical of our subtropical anticyclones. We have the South Atlantic high on the west, and we have the Kalahari high pressure cell on the interior, and we have the South Indian on the extreme east. This is our South Indian high pressure cell. So these are our three anticyclones that affect the weather conditions over the Southern African subcontinent. Right, let's look at our questions. Right, our first question says, name the high pressure system located on the east of South Africa. We have already answered the question by naming, this is the South Indian high pressure cell, or we can call it an anticyclone. It's South Atlantic on the western coast and South Indian on the eastern coast. Discuss the high pressure system mentioned in 131. How the high pressure mentioned in 131 contributes to summer rainfall. How does the South Indian high pressure contribute to summer rainfall in the eastern parts of South Africa? The reason why we have summer rainfall over the eastern coast is because of the influence of the South Indian high pressure. Why is it that it influences the eastern parts to have wet conditions in summer? Right, the reason is it pushes, we are summarizing the reason, moist air. inland in summer. Right, moist air is fed into the interior from the South Indian high pressure during summer season, or we can say onshore winds, the winds which are blowing from the ocean over the interior carry moisture. And what is going to happen? Moisture condenses over eastern escarpment, causing rainfall. Right, so we see the situation here is this South Indian high pressure cell is responsible for pushing in moist air inland. Because it's a high pressure cell, it drives air out of its circulation, and the air is going to be driven into the interior. And the air which is being driven here is going to be carrying moisture because of the influence of the warm Mozambique current. The ocean is a warm ocean. Remember the properties of warm air. Warm air has got capacity to carry moisture. And for that reason, we are saying the air which is being fed into the interior from the South Indian high pressure is going to be moist. And for the reason of the escarpment, we are saying the air is forced to rise over the gradient from the coastal areas to the interior, and is going to condense. As it condenses, it forms rainfall over the eastern area. Right, the eastern parts of South Africa receive rainfall because of the influence of the South Indian high pressure. Let's look at the next question. The next question is saying, when the Kalahari high pressure system dominates the interior of South Africa during winter, residents of Bloemfontein describe typical weather as days starting with cold mornings that warm up in the afternoon with dry air. Right. Explain why the temperatures increase from morning to afternoon. Why the temperature increase? Why do we have low temperatures during the morning early hours? It's because of terrestrial radiation. Or what we call long wave radiation. What is the influence of terrestrial radiation? Is that the heat that has been received during the day is going to be lost at night. Why? Because during winter season, we have clear, cloudless nights. When the sky is clear, it automatically means that the amount of heat which is going to be lost into the space, into the atmosphere, is going to be more. Why? Because clouds are responsible for reflecting back some of the heat. They send back the heat which is being lost from the ground. That is why you tend to find that in early mornings when it's a cloudy night, it's warmer than when it's a clear night. Why is it very cold during clear night mornings? The sky has been clear over the night, but the following morning you tend to find that you even experience frost on the ground. It's because of excessive loss of heat due to terrestrial radiation. But when we have clouds, it means the clouds are going to bounce back some of the heat and it's going to be warmer in the morning. But because of winter conditions, there is limited cloud formation, the sky is always clear, and we have excessive loss of heat, which is in the form of terrestrial radiation. The mornings will be very cold. That is the reason for morning cold. It's because of long wave or terrestrial radiation. They result in cold mornings. Let's look at now the rise of temperatures during the day. We have insolation. As the sun rises, there is now receival of heat. Insolation during the day, it now results in warm afternoons. So that's the trend. We have cold mornings because we have lost heat due to terrestrial radiation, but as the day progresses, we tend to find that there is incoming radiation that results in a positive gain in the amount of insolation. Right, let's go to question number B. That is question number 133B. Why are the weather conditions in Bloemfontein described as dry? Why are they described as dry? Right, if you check it, you see that we look at the influence of the dry adiabatic lapse rate. The air which descends from the escarpment is heating up as it is descending, and it heats up at a dry adiabatic lapse rate. And as a result of its descending, it becomes dry. And also, why is it dry? Is because of the invasion layer. Over the interior. In winter, we have the invasion layer, which reduces moisture being fed into the interior, leading to dry conditions. And also, if you look at it from the winter perspective, there's sinking air. And if air is sinking, that will lead to limited cloud formation. Clouds cannot form if the air is sinking, but clouds can effectively form if we have rising air. So, for the sake that there is limited cloud formation, which can also be attributed to limited condensation. Why? Because there's sinking air. If we have sinking air, we are opposing the norm of condensation. Condensation must happen if there is rising air. The air is moist and is rising. It reaches dew point temperature, and the moisture within the air parcel condenses to form clouds. But in this instance, we are seeing the opposite movement of the air. The air is moving in an opposite direction, it's descending, and however, it implies that the air does not result in condensation. That is why we are describing the conditions as dry. Let's go to number 134. Discuss the negative environmental impact that may be caused by the dominant Kalahari high pressure system in winter. We are looking at environmental impacts. We want to look at the impacts on the environment, on the natural, on the physical environment. What is likely to happen, which is negative on the environment about the dominance of the Kalahari? We understand that when the Kalahari high pressure system is dominant, it leads to dry conditions. It leads to loss of precipitation chances. It leads to clear skies, clear cloudless skies during the winter season because of sinking air. So we look at the influence like decreased rainfall. That's the factor. How does it impact on the environment? It decreases soil moisture. It's a negative implication. The soil must be containing moisture for the sustenance of the natural vegetation. But now, because of the limited rainfall, it means the moisture is limited also in the soil. And also, formation of frost. Which may destroy natural vegetation. We are seeing that there is descending air, there is sinking air, and the air is very cold. And for that reason, it results in the formation of frost, and ultimately the frost can destroy vegetation. There is also a chance of backwinds on the coastal areas. Because of the strong descending air, backwinds might form, and the backwinds might cause wildfires. and the failed fires have got a destructive effect on the environment. We can also look at loss of habitat. Loss of natural habitat. The natural habitat might be lost because of excessively cold conditions. We can also look at it from the perspective of disruption of food chains. The food chains might be disrupted because of the excessively cold conditions. Or we can look at disruption of biodiversity. There are some crop and animal. There are some sort of like natural vegetation varieties that cannot sustain under specific cold conditions, and also some animals that cannot thrive under excessively cold conditions. They might be forced to non-exist, and that is going to ultimately disrupt the balance of nature and the variety of species in a given geographical area. That was question number 1.3. We look at question number 1.4. Question number 1.4 is based on the most cities receive more rainfall than the surrounding rural areas. That's the context of our question. Right, it talks about urban heat islands. Let's go and look at the question. Define the term urban heat island. Right. When we're looking at an urban heat island, mostly learners, they tend to confuse an urban heat island with a pollution dome. The ideas are not the same. When we're talking about an urban heat island, we are looking at the effect of temperatures. How does an urban area's temperature differ from the surrounding rural areas? That is an urban heat. Heat as in temperature. If whenever you're starting to talk about pollution, we are no longer relating to heat. Heat, we are relating to temperatures. So our common definition, we can say an urban heat island. We can say it's an urban area that is significantly warmer than its surrounding rural areas. That's the idea. Or we can say it's an urban area that has got higher temperatures compared to the surrounding rural areas or the farmlands or the countryside. The idea here is to address that an urban area has got significantly higher or warmer temperatures. It's warmer compared to its surroundings. It's having higher temperatures compared to the farmlands or compared to the countryside surrounding it. That's the idea of an urban heat island. We are relating to temperatures here, not anything to do with pollution. It's about temperatures. Describe one human activity evident in the sketch that contributes to the urban heat island effect. We want to identify a human activity. Right. So if we check there, we see that we have industrial activities. They contribute towards the urban heat island. Industrial activities, we are looking at the release of pollutants into the atmosphere. If we see the chimneys of the industries, they are showing evidence of emissions into the atmosphere. What is going to happen with those emissions? They are going to absorb the heat and they are going to cause the temperatures to increase. Right. And also if we check in the city commercial here, we are seeing that there is building density. The density of the buildings, they also increase the amount of heat. So we have dense buildings. They contribute. And also if you look closely, We are not seeing any vegetation in the commercial or the industrial area there. So we also look at removal of vegetation. And also, if you look closely, we are also going to see the influence of tall buildings. If you check the city commercial area, has got very tall buildings, and those buildings are going to ultimately contribute towards the absorption of heat. And also, we are looking at artificial materials. They are the very materials used in the construction of the buildings in the urban area. So all those ones, they contribute towards the absorption of heat, and ultimately there is going to be a very big difference in temperatures comparing the urban setup and the rural or the farmlands or the surrounding countryside as a result of those factors: the dense buildings, the removal of vegetation, the tall buildings, artificial materials that are used, and also industrial activities. Right, we move on to the next question. Identify the natural hazard caused by increased rainfall as mentioned in the article. As mentioned in the article, it is talking about, it says, urban heat island effect is relatively well known. What fewer people know is that the urban heat island has a counterpart with important consequences. Urban development increases the amount of rainfall in an urban area compared to the surrounding rural area. This could have wide-ranging implications, the most serious of which is flash flooding. Flash flooding, I can relate this to the flooding that happens in arid and semi-arid areas, where we experience very heavy rainfall over a short period of time, and we have a very serious flooding effect. Why do we have such type of flooding effect in an urban area? It's because of the artificial surfaces. The water cannot, the rain drops cannot infiltrate into the ground. Why? Because most of the surfaces, they are hard surfaces which do not allow for infiltration. So there is rapid runoff, and that will lead to a situation of flash flooding over an urban area. Right, so our main concern here is flash flooding. Then it says why, explain why there is a rainfall difference between rural and urban areas. Why do we experience more rainfall in an urban area compared to the rural areas? Right, for rainfall to form, we need what we call hygroscopic nuclei for condensation. Hygroscopic nuclei for condensation. We are saying for water droplets to form clouds, when there is water vapor in an air parcel, for the water vapor to effectively to change into water droplets that can result in cloud formation and rainfall, there is need for a nuclei for condensation. The water vapor needs to find a molecule where it has to accumulate itself and form a water droplet. It cannot just form water droplets without having somewhere to condense. So because of the presence of the nuclei of condensation, because of emissions in the urban area, because of dust particles, because of pollutants in the atmosphere, those pollutants, they form part of the hygroscopic nuclei, which facilitates condensation. So it means whenever we have rising air which is moist in an urban area, that rising air is going to effectively condense because of the prevalence of the hygroscopic nuclei of condensation in the atmosphere, which is contributed from industrial activities, from vehicle emissions, and from dust particles which are generated from construction and any other activity that might be happening in the urban area that contributes towards the pollutants in the atmosphere. So for that reason, we tend to find that we have less rainfall forming in urban areas, not because there is no evaporation taking place, but because there is no hygroscopic nuclei of condensation. And for the other reason is because of increased convection. What are we saying? We are saying in an urban area, because of the urban heat island, the temperatures are usually higher in an urban area. And for the same reason, we understand that when the temperatures are high, we tend to have the development of a low pressure cell. And a low pressure cell facilitates the feeding in of air from the surrounding rural areas. As the air feeds in into the interior of the urban area, it converges and it rises. As it rises, it means it is going to lead to cloud formation. So for those two reasons, we are saying the urban area will have more rainfall compared to the rural areas. The rural areas, because of the cooler conditions, have got higher pressure, and they tend to have air feeding away from them into the urban area with low pressure, and the air converges around the urban area and it rises, creating clouds and ultimately bringing in higher chances of rainfall compared to the surrounding rural areas. Right, let's look at question number 1.4.5. In a paragraph of approximately 8 lines, discuss the natural materials and methods that can be used to reduce the urban heat effect. We are going to summarize this. One, we can plant trees. Mainly along roads. Trees have got shade, which help reduce the temperature, and also trees transpire, they add moisture into the atmosphere. We can create green spaces where we add vegetation. For example, we create the parks. And also we can plant vegetation. In unoccupied spaces. Is another measure. We can also use natural materials for construction. Is another measure. Natural materials, they tend to reflect much of the heat than artificial material. We can also install water features. Open water bodies or the fountains, they can help also to reduce the temperature. We can also promote rooftop gardens. Right, those are some of the measures that we can put in place to try to deal with the problem of the heat effect. Let's go to number 1.5. Refer to the sketch below of atmospheric conditions in a valley. This is a typical valley climatic conditions, which are typical of our local climates. We are seeing is typical of a valley area. On the valley floor, we tend to find what is happening there at B, and along C, we tend to find that on the upper reaches of the valley, there's a settlement, and we tend to find that A is air, which is ultimately sinking into the valley floor. Identify wind at A. Wind at A is sinking wind, which typically happens during the night. We call this a katabatic wind. Define the temperature inversion. A temperature inversion is the reversal of the normal temperature profile in the troposphere, where temperature increases with height. Or okay, say it increases with altitude. We expect that in the troposphere, our temperature profile must be negative. The higher we go, the cooler it must become. But if it reverses that, we are finding that the higher we go, the higher the temperatures become. That is an inversion. It's a reversal of the normal temperature profile in the troposphere. Or when temperatures increase with height or with altitude, that is a temperature inversion. Explain how temperature inversion occurs in a valley. Right, how does a temperature inversion occur in a valley? Right, I'm going to use this illustration here to make sense. We are seeing there is cold air on the valley sides. How do we experience cold air at night is because of long wave radiation. There is loss of heat because of terrestrial radiation. Because of loss of heat here, the valley sides become excessively cold, meaning to say the air which is immediately above the valley side, it becomes also cold and it becomes denser. As the air becomes denser, it becomes heavier. Why? Because you are saying if air is being cooled, it gains density, and as it gains density, it becomes heavier. It is going to go down the slope because of gravity. And then in the valley, there is warm air here. But this warm air, because it's less dense, it is going to be displaced. How is it going to be displaced? We are now looking at two air masses, one which is heavier and one which is lighter. Which one is going to occupy the bottom? We mix oil and water. Oil is less denser compared to water. Water is going to occupy the bottom part. And the same happens with the cold air. The cold air is going to occupy the bottom. Where is warm air going to go? It's going to be forced to rise. As the warm air is being forced to rise, we have cold conditions at the bottom and we have warm conditions on the upper part. This is now an inversion. We were experiencing a situation of now cold air at the bottom of warm air. Instead of us having lower temperatures in the upper atmosphere and higher temperatures close to the ground, we are now experiencing the opposite. That is basically how a temperature inversion forms. Because of the sinking cold air, the sinking cold air is more denser. It is going to displace the warm air in the valley, and the warm air is going to occupy the upper part of the valley, and as a result we have a situation whereby the bottom is occupied by the cold air and the upper part of the valley is occupied by warmer air, which gives us an impression of a temperature inversion. Like you can see here, it's 4 degrees Celsius at the bottom. It rises to 8 to 10, which is a situation of a temperature inversion. Right, explain how the wind mentioned in 151 will negatively impact farming. We are looking at the katabatic wind. How does it impact farming in the valley floor? Right, when we're looking at farming activities, we tend to find that the farming activities that will tend to happen in the valley floor are determined by the conditions that prevail in the valley. It results in the formation of frost pockets, which is a most important aspect. We have frost pockets forming in the valley, and crops may be damaged. Because of cold temperatures. Crops that do not resist excessively cold conditions are going to be damaged in the valley floor and they cannot thrive. And also it means it limits the type of crops that are supposed to be grown in the valley floor. We cannot grow any type of crop because we know that some types of crops are vulnerable to excessively cold conditions and they are going to die because of the problem of the frost pockets, which are going to develop in the valley floor. And as a result, we look at issues of the nature of crops which are supposed to be grown. We look at frost-resistant crops can only thrive. You can give examples of wheat. We can effectively grow wheat or can effectively grow beetroot in the valley floor because other crops, they are not going to survive because of excessively cold condition. That is with farming. And the community at large, we are saying the impact a farming community located in the valley. The community, the people at large, besides farming activities, how else can people be affected in the valley? it leads to dangerous road conditions for the community. Visibility is going to be reduced in the valley because of the invasion, the thermal belt which is going to form in the valley, and as a result we have the concentration of pollutants which result in ultimately dangerous road conditions which result from foggy conditions. And also we look at decreased temperatures for the community. If there are excessively low temperatures, it means there's going to be high energy consumption. The usage of energy is going to be high to compensate for the reduction in temperatures. That is going to affect the community. So in terms of farming, we look at frost pockets. How do they impact on agriculture? They can damage ordinary crops, and it limits the amount of the type of crops which can be grown in the valley floor. And also, for the sake of the community, is dangerous on the roads because of foggy conditions which usually are experienced in the valley, and also because of decreased temperatures we tend to have high energy consumptions. Right, let's look at the last question, number 1.5.5. Discuss how temperature inversions in valleys can have a negative effect on the we look at the health of the people living on the slope at Valley C. Let's look at it from the perspective of, right, at C here, we are looking at the edges of the valley. How can people be negatively affected there? Right. If you look at this part here, we are seeing that the temperature is lower, is 44 degrees Celsius, and the highest temperature is 10, meaning to say there is a belt of warm air which is now being trapped between two air masses of cold air from above because of the Kalahari high pressure cell in winter, and also because of the Katabatic from the bottom. These people are within the belt of the invasion. How are they going to be affected health-wise? That is the question. So if we look at these people who are located around that area, the midpoint of our valley, they are going to be affected in these ways. Right, for clarity purposes, I'm going to use the same illustration. We're going to do our discussion and we're going to highlight our responses on the illustration so that we don't lose focus of the question. Right, so we are seeing at C, what is going to happen to people around C? There is trapping of pollutants. The pollutants are trapped because of the invasion layer. The invasion layer is going to trap pollutants. It is going to affect people through respiratory complications. We have respiratory issues. People with respiratory complications, they're going to suffer because of the pollutants. We also look at the pollutants ultimately affecting people with risks of heart attack. Is another implication. People are going to have high chances of heart attacks because of the implication of pollutants being trapped. We can also look at irritation because of the pollutants. They are concentrated. Irritation of the eyes. People with eye complications, they are going to experience very serious irritations, and also some will have nose irritations, and also some will have irritations of the throat. Those are typical complications which are going to develop because of the concentration of pollutants which are being trapped by the invasion layer in the valley. So basically we are looking at respiratory, something to do with the breathing or the lung functioning of the people, because of the concentration of pollutants is going to affect the breathing system of people with complications, and also people with heart problems, they are going to be affected. People with are going to be affected with irritations because of the high concentration of pollutants in and within that particular area. Right. We can say this was question number 1. And we have come to the end of our climate and weather question. We need to move on to question number 2, which is a question on geomorphology. Our geomorphology question number 2, it starts with our multiple choice questions. Question number 2.11, this drainage pattern develops on. We are seeing that the drainage pattern there is dendritic, and our understanding is that the drainage pattern of dendritic, it develops over uniform rocks of uniform resistance. That is where we tend to find the development of our dendritic pattern. Right, number 2.12, it says the following drainage pattern is. We are seeing that there is a focal point, and our drainage streams, they are radiating from the central point, which means this is a high-lying area. It can be a volcanic mountain, and the streams are radiating out of a high-lying area. So this is the opposite of centripetal, which we call centrifugal, or radial. It's the same as radial. The streams are radiating from a focal point, and the opposite is centripetal, when the streams are feeding into a central low-lying area, which can be a swampy area or a lake. Right, number 2.1.3, this drainage pattern is, what kind of drainage pattern is this? Where we see our tributaries are joining the main stream at right angles, and also the streams are bending at right angles. We call this rectangular. Then the next question is, refer to the sketch below and answer the questions. We are seeing these two drainage basins with different densities, X and Y, as points along the strips. And we have drainage basin A and drainage basin B. Right, drainage basin A has a dash drainage density where less takes place. Right, we tend to find that drainage basin A, it has typical of a low density. There are fewer streams, or if we can check it from the perspective of the length of the streams, they become shorter if we cumulatively add them. And also, drainage density where less dust takes place. What is the responsible factor for the formation of the drainage density? We look at the effect of surface runoff. So there is low density, and it means there is less surface runoff taking place. So our item 1 and item 3 is the correct response. The stream order at X in drainage basin A, we need to calculate the stream order at X in drainage basin A. This is stream number 1, an independent stream without a tributary. This is number 1, there's no tributary. Again, this is number 1, and this is number 1. So we are seeing stream number 1 plus stream number 1, it gives us stream number 2. And stream number 1 plus stream number 1, it gives us stream number 2. Then stream number 2 plus 2 at this confluence, it gives us stream number 3. Stream number 3 is being joined by stream number 1. The order does not change. It maintains stream number 3. So at X, we are still at third order. So our stream order is a third order at point X. Right, we look at number 1, 2, and 6. The stream order at Y in drainage basin B will be than at X. If we check there, how is it going to be comparable? At Y is going to be higher. Why? Because we have many streams here, which will lead to a higher order at Y. So we are saying it's going to be higher. And the stream order at Y in drainage basin B will be at Y is going to be higher. And what is going to happen than at X compared to X? Yes. And in drainage basin A, because of what about the surface runoff? It means there's going to be increased surface runoff, or there's going to be more surface runoff. So it's going to be higher, the order, and because of more surface runoff, that results in more tributaries forming. So as a result, we have item 2 and item 3, which is response number C. Right, number 1217 says the drainage basin B will be located in an area drained by dash rivers and dash vegetation cover. We are looking at the nature of rivers. For us to have high density, What kind of rivers must we have? We must have permanent rivers which flow throughout so that the streams sustain and give us a higher order. And also in terms of vegetation, what is the implication of vegetation on drainage density? Vegetation facilitates infiltration, which reduces the amount of surface runoff. And as a result, we have less streams forming when there is a high density of vegetation. So we need sparse vegetation. So we match our corresponding responses with permanent and with sparse, which is item A. Let's go to question 2.2. A V-shaped valley develops through, when you have V-shaped valleys like this, they are because of downward erosion, which we call vertical erosion. Right, number 2.22, the landform that will most likely develop when a river crosses an area with inclined, heterogeneous, soft and hard rock strata. We are likely to experience in that situation. Rapid is also necessary, is also a possible response, and also a waterfall. So in this instance, both of the two, they contribute towards the formation of landforms that develop where we have inclined, heterogeneous, soft and rocks, sudden soft rocks. So in this instance, we can say a rapid can be correct. At the same time, a waterfall is also correct. Because if you look at those two, a rapid is a smaller version of a waterfall, but basically their formation is the same. We have alternating layers of hard and soft rocks. So both of them, they are correct. Right. We move on to number 2.2.3. When a stream cuts through a watershed, a steep-sided valley called a, when you look at a very steep-sided valley, when you are looking at the stream cutting through a watershed is a high-lying area separating two drainage basins. So if a river manages to cut through a high-lying area, it is going to create a typical steep-sloping valley landscape, which is very deep. What do we call this landform? It's called a gorge. Right, dash drainage occurs when a river is older than the landform across which it cuts. When a river is older than the landform, that is typical of antecedents. How does antecedent happen? If a river is older, it implies that the landform has resulted when the river was already there. How does the landform develop? The landform will develop because of tectonic uplift. If a landform is being uplifted, it means the river will try to attain its course through the newly developing uplifted landscape. So when a river is older than the landform, that is antecedents. But when the landform is older than the river, it means the river was superimposed on the existing landform. Like we are looking at a situation whereby the existing height above the landform was higher and the landform was gradually declining towards the landscape. Then the river will manage to cut across. That is superimposition. A river is being imposed on an existing landform. But in this instance, we are saying a river is older. The landform was not like that. But because of tectonic forces, the landform got to be uplifted and the river managed to maintain its course. That is antecedents. Right, we go on to the next question. It's saying 2.2.5. The volume and velocity increases after the river capture in the, that is the capture stream, the one that intercepts headwaters of another river. A crescent-shaped lake that is found along a river in the lower course. Crescent shaped, that is an oxbow lake. We understand how an oxbow lake looks like. Right, this cross section shows a valley before rejuvenation. Before rejuvenation, that is Z. When you look at Y, we have terraces. Terraces are typical landforms that form. Number 228, a cross section of a braided river channel. A braided river looks like Z, where we have these islands. These islands are caused by deposition, and as a result, the river will tend to split its course. It's like a river is blocking itself through deposition, and as a result, the river will tend to branch. We have tributaries within the same, we have distributaries within the same river. The river disjoin and join to form a braided channel. That is typical of the landform that we find because of deposition, and it creates those islands, which is typical of Z. Right, that was question 2.2. Let's move on to question 2.3. Refer to the diagram below and answer the questions that follow. We are looking at this particular illustration where we have an ungraded profile and we have a graded river profile. What is river grading? Right, when we talk about river grading, we are talking about a state of equilibrium or balance. A graded river is a river that has got achieved balance between the rate of erosion and deposition rates. If a river attains a balance, the amount of material being eroded is the amount of material being deposited. We are saying the river is achieved in a graded state. It's in grade, it's in balance, it's in equilibrium. That is river grading. The rate of deposition is the same as the rate of river erosion. Describe two features of an ungraded profile. If a river is ungraded, there is no balance. How does it look like? It has an even riverbed. The riverbed is uneven, it's not smooth. And when a river is it has more erosion. When it's ungraded, erosion is more than deposition. And also when there's more erosion, it means it has a turbulent flow. The flow is turbulent. We cannot achieve a laminar flow. And also we have temporary base level, like the waterfalls or rapids. We have temporary base levels of erosion. They are evident in the river. For example, if you have waterfalls or we have rapids, it shows that the river is ungraded. Those are typical indications that show that the river is ungraded. Name the fluvial landform visible on the diagram associated with the ungraded profile. If you look at this, the ungraded profile, what features do we find? Here, this is a waterfall. And also, if you look down here, we see versions of rapids. So those are two typical landforms that we can witness. We have waterfalls, and also we have rapids. Waterfalls, we can see it, there's a waterfall here. There is a plunging of water, rapid water which is vertically plunging. And also if you see there, it shows that there is a form of some undulating slope which result in rapids. Right, draw a labeled longitudinal profile of a graded river. When you are drawing a graded river, we are supposed to look at it from the mouth, from the source until the mouth. So I'll say this is my source of the river, and this is the mouth of the river. How is the river going to look like if it's graded? A graded river has got a smooth concave shape. That is what you must keep in mind. When you are drawing your river, it must show a smooth concave shape, something like that. The mouth is there. We reach, maybe it's discharging into an ocean. The source is there. The shape of the river must be smooth. A smooth concave shape from the source to the mouth. That is how a river which is graded must look like. So you label your source, you label your mouth, and the shape of your river must be a smooth concave shape. Right, explain how a river achieves and maintains a graded longitudinal profile. How does a river achieve and maintain this grade here? How does a river maintain to balance its rate of erosion compared to the rate of deposition. That is what the question implies in other dimensions. So when you're looking at this, you look at vertical erosion in the upper course. We understand that the river is more energetic in the upper course. It causes steep valleys. How do we compensate for the steep valleys? Because there is headward, there is a vertical erosion. We also look at the instance of headward erosion. It removes temporary base levels. In upper course, if there is any temporary base level, they are going to be removed by headward erosion, or that type of erosion responsible for migrating the source of the river. And then as we go, we also look at downward erosion or vertical erosion. It removes temporary base levels. Temporary base levels are removed. For example, waterfalls in upper course. Why does a waterfall migrate upwards? Is because of vertical erosion. We keep on eroding the hard and resistant rock on top of the softer rock, and the waterfall migrates upwards, and it means we are removing the temporary base level, leading to the attainment of a grade. And then where does the material go? Eroded material from the upper course is transported downstream. All the material being deposited from the temporary base level is being transported downstream. And also there's lateral erosion or sideway. In middle course. All the material which is being eroded laterally in the middle course, and also the material coming from the upper course, it is now going to cause the gradient in the middle course to become gentle. It becomes less steep. And then ultimately, the material is going to be deposited as we go into the lower course. It fills up the lakes and dams. So that's basically how we achieve a grade. We then achieve equilibrium, because we have material being deposited in the lower course. The material being eroded in the upper course is ultimately carried downwards. Because of vertical erosion in the upper course, we tend to find that the temporary base levels are being eroded to achieve a grade. And also because of headward erosion, some temporary base levels are going to be eroded. And that material is going to be added to material which is going to be eroded laterally in the middle course because of sideway erosion. And the combined erosive eroded material from the upper course and the middle course, they are apparently going to fill in those other depressions in the lower course, such that by the end of the day, we achieve a grade, we achieve a smooth concave, whereby the steepness is steeper from the onset, from the mouth, and it declines in terms of gradient, and ultimately it becomes a gentle gradient as we approach the mouth of the river course. That is basically how we achieve a river, a grade in the longitudinal profile of a river. Right, we move on to question 2.4. Start the picture below on natural levees and answer questions. It shows us the natural levees, which are raised embankments on the sides of the river channel. Right, what are natural levees? We can say natural levees, basically they are raised river banks. How do they form? Formed when a river floods repeatedly. When a river floods repeatedly, and deposits material on the river banks. Right, that's basically levees. This is the river channel we can see from here. This is the discharge, and we are seeing that the level of the river bank is there, but we have this raised embankment here. It's raised. Why? Because of deposited material. When the river overfloods its banks, it tends to deposit material along the channel. That will create a raised river bank, which we call the natural levees. They are created because of subsequent sessions of flooding along the river channel. When a river overfloods its banks, it tends to deposit material on the sides, and that will ultimately cause a raised embankment along the river channel. In which course of the river are natural levees found? The natural levees are mainly found in the lower course of the river. Which fluvial process results in the formation? They are formed because of deposition of material. Describe the size and texture. Right, when we're looking at the size of the material, mainly we are looking at large particles. But to be specific, we tend to find that the size differs. We tend to have large size particles close to the river bank, but finer material will be deposited further away. Then also we look at in terms of texture, we are referring to particles having a coarse texture. Finer material will be deposited further away, but the coarser material is going to be deposited just along the river channel. Right, discuss the physical impact that the development of natural levees has on the river channel and the floodplain. So we want to look at the impacts on the river channel. How does the development of the natural levees impact on the river channel? On the river channel, we tend to find that the volume of water, or we can say the discharge. What is going to happen to the discharge or the volume of water is going to increase. How does it increase? I'm going to make use of the illustration. If this is our original and our initial volume of discharge, which can be transported in this channel, automatically it means if the level rises above this without the levees, the water is going to overflow the river banks. But now the new level is there, and the new level is now there. It means we now have extra capacity of the river to increase its volume of discharge. Why? Because we have raised embankments along the river channel. So the volume is going to increase, and also we look at the velocity is going to increase. As the volume increases, it also means the velocity is going to increase. And also the carrying capacity. The waters, the level of the amount of material being carried by the river is going to increase, which we call the carrying capacity. Why? Because there is now large volume, and also there is now more velocity. It means that the carrying capacity is going to increase. The river is now able to carry more load, and also we are going to have a deeper channel. The channel is going to be deeper. Right, then we look at, this is how about the river channel. We also look at the floodplain. How is the floodplain going to be impacted? When we are looking at the floodplain, we are looking at the flat adjacent area to the river channel. We are looking at reduced deposition. Of silt material. Why? Because now the river is raised. It does no longer flood on the like floodplain, and also the risk of flooding. It ultimately decreases because now the river is confined to a defined channel. There is now less water, which is likely to cause flooding on the floodplain. So there's also flooding being reduced because of the raised embankments, which are going to contain water, or which are going to confine water within the channel and reduce the risk of water overflowing into the adjacent flat lying area. Right, that was question 2.4. We need to move on to question 2.5. Question 2.5 is talking about an ecological disaster on the Bluesbanksprut, which is a typical case study in Krugersdorp. Right, let's look at the questions. What is the main source of pollution in the Bluesbanksprut? Right, if we check there, we can see that it's talking about sewage spilling into streams and rivers from dysfunctional pump houses in Krugersdorp. That is the major source of pollution in the Bluesbanksprut. So we're having a situation of sewage streams and rivers from dysfunctional pump houses in Krugersdorp. The next question is saying, quote two phrases from the extract that proves that the pollution of Bluesbanksprut is an ecological disaster. How is it a disaster on the ecology or on the balance of nature? Right, number one, it says, talks about the pump station, talks about how it is not working. Then it goes on to talk about that there are no signs of life to be seen anywhere around the stream. It shows that the ecology is disturbed. The balance of nature is disturbed. There is no more life or sign of life to be seen anywhere around the stream. And also it continues to say, none of the bird life that is normally associated with the place like this can be observed. It was just smell the eerie colored water and the stench, which is just remaining. So it means ultimately that the ecology has been disturbed. If there is no evidence or there is no sign of life, it means the ecology has been disturbed. There is no more sustenance of natural life because of pollution. And also bird life, the birds which used to thrive along the river, they are no longer there. We are only now experiencing just the smell, and we are also experiencing this eerie color of the water and the stench, the smell which is coming from the polluted water resource. Right, taking it to the next question, number 2.5.3. Account for the ecological disaster in a Bluesbanksprut. We are saying, what is the reason for the ecological disaster? Where is the problem coming from? Right, if we check in our source, where is this typical problem coming from? We are looking at a dysfunctional. Right, it talks about a dysfunctional pump house in Krugersdorp. A pump which is no longer working is causing the problem. And also it continues to tell us about other sources of the problem. It talks about the issue, a pump in Massenville looked after by a loan security has not been operating for months. The controls now use self-boxes as pair of old boxes. Just behind the pump in the field, the stream of sewage meanders its way into Blankspetersroute, which flows from Krugersdorp through Coronation Park. The Krugersdorp CBD through Massenville. We are looking at the route right. So we are looking at the typical problems which are now being experienced there. We now have all but defunct P.1 wastewater treatment plant. There is a treatment plant which is now not working, and that is going to impact on the ecological aspect of the ecosystem in that particular area. The defunct P.1 wastewater treatment plant is also another cause. And also, if you look at it from the perspective of the picture of what is implied there, we can also look at it from the growing population. If you look at Massenville as a location, we see that it is growing, it's a rapid growing urban center, whereby the population is no longer in line with the planned infrastructure and ultimately is giving pressure on the available infrastructure. And also we can look at other measures, the other sources of the problem. We can also look at misuse of funds from the municipality. Funds which must be allocated towards the resustenance of water reticulation and sewage treatment plants is also being misused, and as a result, we have typical problems. We also face the typical problem of corruption within the government entities, where the funds are being used for personal gain instead of supplying the basic necessities for the societies. So as a result, we tend to find that we have typical problems of such ecological disasters. And also can look at poor maintenance of infrastructure as another issue that can be attributed towards the cause of the ecological disaster. Then our last question is saying, in a paragraph of approximately 8 lines, suggests measures that the municipality and the local community can implement to avert this ecological disaster. What can we do to do away with this disaster? We can make use of awareness campaigns. Let us do awareness campaigns to educate the people and make the people be aware of how dangerous is it to affect the ecology. We also look at water quality monitoring to ensure that the water quality is maintained. We can also look at maintenance of septic tank systems to ensure that there are no leakages. It's also a measure. We can also improve wastewater treatment before it finds its way into the ecology. We can improve on wastewater treatment, and also can look at other measures like regular cleanup, can also try to do that. We can also try to implement buffer zones to limit the human activities on the rivers. We create boundaries, boundaries that limit the implication of human activities into the rivers. We try to limit the impact of human activities onto the river and ultimately try to reduce the amount of pollution that can be added to our water resources. There are many things that can be talked about. We can talk about a number of measures that can be put in place as a way of sustaining our ecology. But for the sake of our discussion, we can limit ourselves to those ones, but there are a lot more that we can talk about, including education campaigns, also including law enforcement, also including use of fines, heavy fines to those who are polluting the ecology, mainly if you look at it from the perspective of the business people, or also if you look at it from the perspective of households. We are trying to establish a safer dumping sites so that we do not influence the activities of human dumping to the rivers. Right. We move on to our next section. With question 2.5.4, it takes us to the end of section A, which is our theory section on geomorphology. Question number 2. We move on to our geographical skills and techniques, which is our map work section. Right, our map is based on Harrismith. There is map information there. Harrismith is a town in the Free State province of South Africa. Whatever is there, you need to understand the map information, as it is going to guide you in answering some of the questions. But our first question is saying, in which province is Harrismith located? Where is Harrismith located? We have already found out from the map information that Harrismith is located in the Free State. The contour interval on the orthophoto map, we just have to go to the orthophoto map, but that is common understanding, that is common knowledge. The interval does not change for the orthophoto map and for the topographic map. What you call the interval is the difference in height between two contour lines next to each other. Like we are looking at this contour line and the next contour line. What is the difference between their height? They differ by 5 meters. That is the contour interval for every orthophoto map. And for a topographic map, the interval is 20 meters. Right, refer to the topographic map. Calculate the distance between trigonometrical station 299 in block C2 to spot height 1983 in block B5 on the topographic map. So we are looking at the two features. We are looking at topographic station in 299 in block C2. Let's go to our maps and look at our topographic map. We want to refer to block C2. Our block C2 is here. We want to look at a trigonometrical station number 299 is here. I think you can see it. This is where our trig station is. And we are looking at the other perspective from B5. Our block B5 is there. We want to relate to a spot height 1983. We can see that our spot height is there. So what do we need? We need to calculate the distance between the two. So for us to calculate the distance, we need to measure a straight line distance between these 2 points. Straight line distance between the two. Make sure when you're placing your ruler, the beginning point or the starting point must be reading 0 on your ruler, and the last point must be on the dot of the spot height. Then you are able now to figure out your distance. So without wasting much of our time, we are saying our distance, the accurate distance must be plus or minus 9,9 centimeters. Then we multiply the distance by the map scale. We want our answer to be in which measurement? Our question is saying the map distance is supposed to be calculated in the actual ground distance. So there's no specific measure here. So if you want to, for conversion on a topographic map, just for highlighting purposes, if you're using a topographic map, if you want to convert your distance to meters, you multiply your centimeter measurement times 500 meters. If you want your distance in kilometers, you multiply your centimeter measurement times 0.5 kilometers. So here our question is not specific, it's just saying calculate the distance, which means an answer in meters is going to be correct and an answer in kilometers is also going to be correct. So our correct and accurate measurement is 9.9, and for the sake of deviance, we accept 9.8 to 10 centimeters, but not anything else outside the range of 9.8 to 10 centimeters. You must be very accurate in your measurement. So if you are using 9.9, if you want our answer to be in centimeters, we simply have to multiply this by, in meters, to multiply by 500 meters. Or if we want our answer to be in kilometers, is 9.9 centimeters, this is going to be multiplied by 0.5 kilometers. So your measurement is going to give you these figures for 9.9 times 0.5 is going to give you your measurement, and also for 9.9 times 0.5 is also going to give you your actual distance in kilometers. And for the sake of our deviance, we've allowed it to be varying from 9.8 to around 10 centimeters. Right, that is how you convert your distance. There is no specific measurement, but what you need to know is the conversion. A scale of 50,000, you multiply by 500 to convert your actual distance to meters. For a scale of 1 to 50,000, you multiply by 0.5 to ultimately convert your measurement to the actual distance in kilometers. Let's go to number 3.1.4. Calculate the present magnetic declination for 2026 on the topographic map. Right. We use the map information at the bottom of the map, but ultimately our annual change is given. So what do we need to do? We need to calculate our difference in years. We want to calculate for 2026. What is the map information provided? Which year is used, or which base year do we have for the map? If we check on our map, it says mean magnetic declination was 22 degrees 36 minutes west of true north as of March 2018. This is our year for the map, 2018. So if you want to calculate the difference in years for 2026, we are now saying we are in 2026. Our difference in years is going to be 2026 minus 2018, which gives us a difference of 8 years. Then we go on to calculate total change. We are saying how many years have lapsed since 2018 to the current year. Our total change is going to be, the number of years is going to be 8 years, times what is the annual change. For every year, our position of the magnetic north is changing by 16 minutes further to the west for each and every year. So we multiply by 16 minutes to the west. And that is going to give us a total of 2 degrees and 18 minutes to the west of true north. Then we want to calculate now the present declination, the magnetic declination for 2026. We are saying the angle which was there in 2018 has further increased to the west by the total change which has been realized over the last 8 years from 2018 to 2026. So we are now adding the angle which was there in 2018 to the accumulated total change over the 8 years. So the angle which was there, if we check from our map, we see that the angle of declination in 2018 was 22 degrees 36 minutes to the west of true north. So we are saying that old angle for 2018, we add it to the accrued total change over the 8 years. So we are saying it's 22 degrees and 36 minutes. We add the accrued total change over the 8 years plus our 2 degrees 18 minutes, which have been realized over the 8 years. How much does it going to give us? It is going to give us 24 degrees and 44 minutes to the west of true north. This becomes our correct response. So you must make sure that you follow the steps of calculating the present declination by starting by actually figuring out the difference in years from the map year to the current year that you want to ascertain the declination. We are using 2026. So we are saying 2026 minus 2018. That gives us a total of an accrued time frame of 8 years. And for those 8 years, we are saying for every year in those 8 years, our mean declination was 16 minutes to the west, which means for every year it was changing by 16 minutes going further to the west, which means we are finding a total change over the 8 years by multiplying the 16 annual change by the number of years which have lapsed, which is 8 years, we get our total change. Now, for us to find the new angle, we are now saying what is the accrued total change over the 8 years plus the angle which was there in our map to find the current declination. I think that is understandable. Right, let's go on to look at question number B. Calculate the present magnetic bearing for 2026 from spot height to spot height. Use the following information. The true bearing. We are given the true bearing, which means we must not waste our time. If we want to find magnetic bearing, we are now saying the true bearing plus the magnetic declination for the given year. So our true bearing is 218 degrees. We add it to the current magnetic declination angle, which we found is 24 degrees and 24 degrees and 44 minutes. What do we get if we add this? We are simply going to get 242 degrees and 44 minutes. As simple as that. Right, discuss the importance of calculating the present magnetic declination for aviation for those who fly. Why is it important for them to calculate the present magnetic declination? So that they will not get lost. Remember, as they are flying, they are using magnetic compasses. If they use a wrong angle, they will go to a wrong place. And also we can say it is the most accurate direction. For them to ascertain where they are going, they must use the current so that they will be able to identify exactly where they are supposed to go. Right, we look at map interpretation question number 3.2. Question 3.2.1 says refer to F and G on the topographic map. Which area F or G will have lower temperatures? Let's look at the two places. We are referring to the topographic map, area F and area G. Area F, we can see the built-up area. And let's look at area G. Area G is a natural area. So, which area will experience low average temperature? This is a built-up area. This is a natural area. So, automatically, we see that the area which is going to have lower temperature is going to be G, for the same reason that we have natural surfaces. And in F, we have artificial surfaces. So artificial surfaces will absorb heat, while its natural surfaces will be responsible for reflecting heat and will be giving a cooler condition. Provide evidence from the topographic map for your answer. I think we have actually expressed that. Our answer is G. It has natural vegetation. Which cools the temperature. And if you look at G, what is the problem? It's a built-up area. So because of that, we tend to find that these two places, they tend to have a difference in temperature. Then refer the topographic map on the orthophoto map. And the orthophoto map, identify river 6 found in block B2 on the orthophoto map. We want to relate the two. Identify river 6 found in block B2 on the orthophoto map. River 6, left 6, let's look at it from the side of the orthophoto map. Our 6 is there. This is our river 6. Along this, what is this river? The name of the river is here. It's Filch River. According to our map information, the river is labeled here. It's the Filch River. In which direction does the river identified flow? Where is this river flowing towards? We need to integrate the orthophoto and the topographic map. Let's go to our topographic map and try to see the direction of flow of the river. This is the very river that you are talking about. So where is this river flowing towards? In which general direction does the river flow? This river is flowing in this direction. It's going to the northwest. The river is flowing towards the northwestern direction. What is the evidence? For us to figure out the evidence, we check the tributaries. And also we check the heights. What about the tributaries? Let's look at the tributaries on the topographic map. If we see our tributaries are joining at acute angles from the side of the southeastern direction. So it means if tributaries are joining like this, the river is going in that direction. It must give you a clue by looking at how the tributaries are joining. We understand if it's dendritic pattern, if a stream is going this direction, the tributaries will join from the opposite direction, which means this river is going that direction. So in the same sense, our tributaries are joining at these angles. If you check here, our tributaries, the acute angles are facing this direction. So it means the river is ultimately going in that direction. And also you can check clues of height. If we see any clue of height, you see here, the spot height is 612. And we see as we go, there's another one, it's 16. This one is 1612. This one is 1603. It means this is a high-lying area. And this means it's a low-lying area. So rivers, we understand they flow from high-lying areas going towards low-lying areas, except where there is antecedence or where there is superimposition. But in this instance, our general direction of the flow of the river is northwesterly, because we see the river entering the map at this height around. Also, if you check, there is 1631, which means this area is higher compared to this area. So the river automatically is flowing from a higher lying area going towards a low lying area. Right, we continue and look at the next question. Identify the fluvial feature 12 in block D4 on the orthophoto map. Right, let's look at block D4 on the orthophoto map. The fluvial feature 12, this one here. This is where we find our fluvial feature 12. What is this feature? We are seeing that our river is bending like this. So what is this feature that is resembling a bend along the river channel? So this is a meander. Identifying the fluvial course of the river where feature 12 in the above answer is located. Our meanders basically form in the middle course of the river. The river winds up in the middle course. Draw a labeled cross section through line 8 to 9 in block C2 and C3 on the orthophoto map, indicating the main fluvial processes. We want to look at label 8 and label 9. This is our cross section. Right, I'm going to transpose this to a clear space. Right, we are seeing that our bend looks like this. Our point 8 is somewhere here, and our point 9 is somewhere there. And how is our river looking? Our river is like bending like this as a general sketch. Right, our point 8 is here, our point 9 is there. We want to draw a cross section from point 8 to point 9. Right, what we need to understand here, this is what we call an outer bank of the meander, and this is what we call an inner bank of the meander. What happens here is there is first velocity of water, and there's going to be erosion happening on the outer part. And here, there's going to be slower velocity of water, and there's going to be deposition. As a result, we have what we call an undercut slope. And here, we have what we call a slip off slope. Right. Why? Because the water is being forced to immediately bend here. It is going to reduce velocity. But here the water is going to have a more straighter course because of the nature of. So water flows faster here and it flows slower on this side. So as a result, if you are to draw a cross section, we are saying if our point 8 is here and our point 9 is there, it means there is going to be a general gradient because of deposition of material from point 8. But as we go into the channel and approach point 9, there is going to be an undercut slope which is going to happen. So when you are labeling here, we say there is deposition taking place, which gives us this general slope. And there is erosion taking place. Those are the fluvial processes on either side. And what is this deposition going to give us? It is going to give us what we call the slip off slope on this side. And it's going to give us what we call an undercut slope on the other side. That's basically what you need to understand. So our point 8 is there, our point 9 is there. Where there's an outer bank, we have this typical of processes happening. Where there's an inner bank, we have those processes happening. That is basically the picture of what you must figure out from the illustration. Right, we are done with our question number 3.2. We now have to move on to GIS. Right, define the concept data layering. Right, when we're talking about data layering, we are referring to a situation when different spatial data layers are superimposed on each other. To form an integrated image. So when we're talking about data layering, we are saying we are superimposing data layers. We are putting data layers one on top of the other to ultimately give an integrated approach to show how the data layers relate to one another. What we call a data layer is a thematic layer which shows specifically one geographical aspect or one geographical set of data. So we want to compare how those different data layers interrelate with one another. So we superimpose or we put one layer on top of the other to show an integrated approach of how those data layers relate to one another. Or we can define it in any other geographical sensible way. Right, number 3.32, it says data manipulation or data standardization involves the process of converting data to a common format. When we are converting data to a common format, we are standardizing the data. Like for example, our map symbols are standardized, meaning to say, if you're in South Africa, you are able to read a map from America. You are able to read a map from the UK. You are able to read a map from Zanzibar. Why? Because the maps are standardized. We use a common scale for our topographic maps, 1:50,000. We use a common scale for our orthophoto maps, 1:10,000. We use common conventional symbols for specific geographical features, which means the maps are standardized. We are able to read those maps because they have got common and understandable formats that are used. We use conventional signs. We use conventional colors. We know green is for vegetation. We know constructed features in black or in red. We know. So it's like we are making universally applicable. We are making maps universally applicable. We are making the data universally applicable. So that whenever we use the maps, we are not worried about where the map is coming from. It uses the same format. We use the similar conventional symbols. We use the same scales. That is data standardization. Right, choose the correct answer from the brackets. We have chosen the correct answer. Use the following extract from block B5 on the topographic map to answer the questions. Refer the vector data in the extract and identify one example of a natural line data and one example of a man-made point data. Right, if you're looking at this, we want to identify one example of a natural line feature. If we check a natural line feature, this is an extract from, let me use the topographic map, block B5 from the topographic map. Right, we go to our map, we go to block B5 from the topographic map. If we come here, our block B5 is here. Right, this is our referral block. This is our block B5. We want to identify a natural line data and one example of a man-made point. If you look at this, this is a line feature, which is natural. And also, if we look at this, block B5, this is a natural line feature. So what are we saying? We are saying, what is this feature here? This feature and these features are the natural line features. Then we want to identify a point data feature. If we check here, our point data feature is this one, which is a spot height. So coming back to our question, our two features, we find them. One is here, and also the other one is there for a line, and the other one for a line is also there. So what is our example of a line? Our line features, we have a row of trees, as shown here. And then another line feature, we have our non-perennial river, which is shown by this broken line here. It shows a non-perennial river. These are our two line features, which are natural. Trees are natural, a river is natural. Then we want a man-made point feature. Our man-made point feature, automatically, we are seeing we have a spot height. Those are our two features. Two for a line feature, which is natural, and one for a man-made, which is a point feature. Then we come to draw two adjacent blocks as shown in the below answer book. Use the concept of paper GIS and draw the following two adjacent blocks. We want an infrastructure data layer in A, and in B, we want drainage data layer. Right, so what you must understand there is we need to figure out infrastructure in the block in question. What kind of infrastructure do we have? If we check here, this line is indicating a road, and a road is part of infrastructure. So it means we must draw this road. That is the only layer of infrastructure that we have in this particular block. We must try to trace out, using paper GIS, to trace out the shape of this road and portray it in the given a block for infrastructure. So we are saying our A, we want to portray our infrastructure. We want to ultimately transpose or trace this road into this block, because that is the only infrastructure layer that we have. We don't have like a railway line. We don't have buildings. We don't have a power line. Those are forms of infrastructure, but the only layer that we have there, it constitutes under infrastructure, this road. So we are supposed to draw the same road as it is shown on that particular block. So our road looks like something like there. It starts from there, it goes. It might not be accurate, but we want to try to portray the shape, and it goes out of the block like that. This is our A, our infrastructure layer. Then we go on to our drainage layer. Drainage, we are looking at water bodies. What water bodies do we have in this particular block? Which water bodies can we figure out? If we check closely by looking at this, or by looking at the topographic map, we can figure out that we have this non-perennial river, this one, and we also have this non-perennial river here. They are joining somewhere there. So tracing this, and also if you check close to the end of our block, there is also another non-perennial river there. Those are our indications of drainage data layers from that particular block. So we want to trace this and this into our new block. So tracing that, it looks like something like our non-perennial river. It goes something like, it gives us a shape, something like this. It goes and it gives us a picture, something like this, somewhere there. And also if we check to the bottom right corner, there is also a non-perennial river which crosses somewhere there. That is basically what is required for the paper GIS for those two blocks in terms of infrastructure and also in terms of the layer for drainage. Then our last question is saying, why are data standardization and data manipulation important when performing data layering? Why must we have maps which are standardized or which are manipulated to facilitate data layering? Right, the reason there is transforms data into a uniform format. And improves accuracy. What are we saying? If we're not using uniform format, or if we're not using the same scale here for this instance, we are saying this block is drawn according to a different scale from the topographic block. It means it was going to be wrong for me to draw the same road as it is appearing here because of the differences in scale. If we're not standardizing the scales, it automatically meant that what I was supposed to draw basing on the scale, maybe I'm using a larger scale and I'm transposing from a smaller scale, automatically that was going to be giving us an inaccurate appearance of the data layer. But if we are standardizing, we are using the same format, we are using the same standard of the data sets, then it automatically means that we are going to achieve a uniform format. Whatever we're going to do there, if we are using a scale of 1:50,000, it means automatically for every map we must be using the same scale. Automatically it gives us an accurate impression, and also it's going to give us a uniform impression. Unlike if you are using standardized data sets, or if we don't manipulate, manipulation is changing the data set to suit the needs of the desired users. If you want to use a scale of 1 to 50,000, let us change the scale. If it's 1 to 10,000, then we must change it to suit the needs of what we want to address. So it makes data uniform, and also it improves accuracy in reading and interpreting the information on the different maps in our question. Right, that brings us to the end of our discussion, and that brings us to the end of our Geography Junior Examinations Paper 1. I hope this discussion is going to take you all along in your preparations for your upcoming examinations, whether it's prelim examinations and also be it the coming National Senior Certificate examinations, which are just coming. Let it be useful, let it be productive, make it worth it, make it as a referral point, and also try to embrace the ideas that we have incorporated in this discussion to adjust them and to manipulate them into the given set of questions, because we understand that questions are just recycled, but the main ideas remain the main ideas. Geography remains geography, and you need to apply the geographical knowledge to the given question. But however, the basic ideas will still remain the same. With that being said and done, I can safely conclude that we have come to the end of this discussion. Thank you for watching. Your host in Geography will meet in other upcoming discussions.
Welcome to Thundereduc, an online learning platform powered by professional, highly skilled and qualified educators.
We deliver structured CAPS online lessons for high school subjects including mathematics, physical sciences, life sciences, geography, business studies, history, accounting, English, Afrikaans, and others.
For the intermediate and senior phases, we offer expert teaching in natural sciences, mathematics, social sciences, English, and EMS, designed to build strong academic foundations.
Access the distinction material books by clicking join button on our YouTube channel or download Thundereduc app on Google Play Store.